Hey, Chemistry 12 class, Mr. Lum here, and this is your video answer key for this next chapter called Bronsted Lowry acids and equilibrium and all that kind of stuff. So, anyways, we have our worksheet right here, and we're going to go through this. So hopefully you watched the video and you somewhat understand this and you've attempted it, and then now you're just checking it over. So write the formula for a proton. Now, if you watch the video, a proton is, well, if here's a hydrogen has, if I were to draw like a Bohr model, a hydrogen has, on the periodic table, it says like 1.0, something like this. And it says the number 1 right here. This number 1 right here represents how many protons it has, and this is the protons plus the neutrons. So this is protons, and this is protons plus neutrons. Since these numbers are the same, that means hydrogen doesn't have any neutrons. So it's just one proton with one electron. Okay? So if you want to write the formula for a proton, well, all you have to do is write the formula for a hydrogen minus that electron. So if you take away that electron, right, then you're just left with that. Or in other words, if here's a hydrogen and you take away that electron, you're just left with a positive right there. So H plus. That's the formula for a proton. Now, a hydrated proton. What's the formula for a hydrated proton? Well, hydrated means adding water to this. So you just take your H plus your water, okay? And that makes, well, H2O plus an H plus, that makes H3O plus. This is a hydrated proton. Another term for a hydrated proton is the hydronium ion. H3O plus, just like that. Okay. So next one right here, it says give the equation HCO3 minus plus H2S turns into H2CO3 plus HS minus. The acid on the left side. So we're going to take a look at this one and this one. So an acid, remember, donates protons. Okay, so it gives up those H pluses. So this one right here, as it turned into this one right here, did it give an H or did it receive an H? Well, it goes from H to H2. So that means it got an H. It received an H. It did not give one. So it is not an acid. This one started with 2, and then it had 1. So therefore, it gave an H. So the acid right here is H2S. Since it is a donator of hydrogens or a donator of protons, then that means this one right here is an acid. If this is the acid, this one right here received, and so therefore it is the base. Okay. Now the acid on the right side, okay, is going to be this one right here. If we look in the reverse direction, as it goes backwards, because this is an equilibrium, if it has H2 and it's going in this direction, it's going to go to H. So it will be losing a proton. So the acid right here is H2CO3. And then the base right here, if this went in the reverse direction, it goes from HS minus, and then it goes to H2S. That means it must gain a proton, and that makes it a base. So HS minus is the base on the right side. Okay. Find the conjugate acids of each of the following. So if it says find the conjugate acids of each of the following, remember, these are all bases. Okay? Bases gain an electron. So we have to add, gain a proton. So we have to add a proton to all of these things. So this one would be H2PO4. Since we added a plus, it used to be a 2 minus, so now it's just a 1 minus. Okay, so this is the acid right here. Because if this H2PO4 turned into this, it would have to lose or donate a hydrogen. So that makes this one right here an acid. And then if this H2PO4 turned into HPO42 minus, this one would have to, H2PO4 would have to lose a hydrogen. And then this one would be the conjugate base pair. Okay, this one would be gaining. Again, if this is the base PO4, okay, and that means this one would be HPO4 2 minus. Okay. If this HPO4 turned into this one right here, this hydrogen would have to be lost, okay, in order for it to turn into PO4. So that would make this acid. If this PO4 3 minus had to turn into HPO4, it must gain a hydrogen, and so that would make this one a base. Okay, so essentially what we're going to be doing with all of these ones right here is if we're finding the conjugate acids, that means all of these are bases. And that means you just have to add a hydrogen to all of these to find the conjugate acids. So we're going to add a hydrogen to this, H2SO4. Okay. And every single time I add a hydrogen, I have to subtract one of these negatives. So NH3 would become NH4, how I had to add the hydrogen. So it's H3 before. But I'm not just adding a hydrogen, I'm actually adding H plus. So this was H3 with no charge, and so I'm adding that plus one, so it has to be NH4 plus. I add that plus one again to this one, so H3PO is only -1, so now it's just nothing. Now same thing for this one. These are all the acids. I must find the bases over here, so I must take away a hydrogen. So this is H2, now it just becomes HPO4. Now, before it was just 1 minus, now it's going to be 2 minus. Okay, this is H3, so now it becomes H2. PO4 is nothing before, it's just 1 minus now. Take away the H, so it's HSO4, so now it's just SO4. It was 1 minus before, so now it's 2 minus. H2O, a lot of people want to write this, HO minus, please don't do that. It's hydroxide, okay? So we kind of write it like that. This is the kind of the one exception how we have to change the formula a bit. Next one, we have to take away that hydrogen again. Take away the hydrogen again, so it would become PO4. Instead of 2 minus, it becomes 3 minus. Okay. Now, give the correct formula and names of amphiprotic anions. Don't forget that anions have to have a negative charge. And the reason why I say amphiprotic anions, because you could write down H2O, but H2O is not an anion because it doesn't have a negative charge. It is amphiprotic, but it is not an anion. Now, this can be a little bit difficult, and I'm going to show you a quick way to do this. If you want something to be, well, first off, you can pretty much make anything up. I shouldn't say that. You can design your own amphiprotic anion. All that it has to have is a free hydrogen, and a negative charge. So say if I take something like H2CO3, okay? Now, H2CO3, this is not amphiprotic because does it have a free hydrogen? Yes, it does. Does it have a negative charge? No, it doesn't. So if I took away a hydrogen from this and just had HCO3, since I took one hydrogen away, it's going to leave a negative charge. Is this amphiprotic? Absolutely. Yeah, it totally is amphiprotic because it has a free hydrogen and it also has a negative charge. So I'm going to write that in there. HCO3 negative. Okay. Now, if you have a hard time looking these things up, what you can do is, here, let's go put that over there, and we're going to open up this one. So this is my data table. Here's KSP stuff. We're going to go all the way down, and now we're going to be taking a look at these things right here. So first off, I put HCO3 minus. I'm unsure of what the name is of it. So what I have to do is I have to find where HCO3 minus is on this table. And I should be able to find it. And there it is right there. Now, on this table, on this side right here are the acids, and this side right here are the bases. So here's that HCO3 minus. It's a hydrogen carbonate ion. I'm going to write that right here so I just don't forget. Hydrogen carbonate. Carbonate ion. Okay. Now, another way that I know that this is amphiprotic is that I see it as an acid, because amphiprotic means acid and base, and I also see it as a base right there. So we know that HCO3 is amphiprotic because, again, it's an acid and it's a base. Okay, so we can find other ones that are fit that criteria right here. So here we find HSO4 minus. It has that free hydrogen. It has a negative charge, and hydrogen sulfate ion. A little messy. It's here as an acid, and HSO4, no, this one is HSO3, so HSO4 minus, it can also act as a base. Okay. Let's take another look at another one. Here's one right here, HSO3 minus, HSO3 minus, okay, hydrogen sulfite ion, hydrogen sulfite ion, and it's there, HSO3, and it's also there, HSO3. So it's on both sides. It's an acid and it's a base. Okay, and there's a lot more examples than just what I'm doing right here. Like I could do HPO4 right here, 2 minus. That's a possibility. I could do H2PO4 minus. I could do HC2O4 minus. These are all different possibilities that I could use for finding something that is amphiprotic. So I'm going to just pick the first one that I found, and that's HPO4 2 minus. HPO4 2 minus. The name of that is monohydrogen phosphate ion. Monohydrogen phosphate ion. And remember, I'm just purely getting the names from my table. Okay, we know that it's amphiprotic because it's an acid, HPO4 2 minus, and we see it also here, HPO4 2 minus. It has that free hydrogen. It has a negative charge. The negative charge is 2 minus, but a negative charge is a negative charge, so it works. Okay, so there is your answer key for this section right here. If you have questions, you can always message me through Teams. Yeah, anyways. And once you feel comfortable with that, please attempt the quiz.